In this video, we are going to discuss various types of trees. There are, in fact, like hundreds of different types of trees, which are like different data structures. I'm not talking about real world trees, but just like data structures. We can't discuss everything in course, so we are going to just discuss the generic types or the most frequently used ones that back up, uh, that kind of work as a back end of various different applications. We are just going to see some of the natural definitions from mathematics about some different types of trees, and then we are going to cover specific computer science types of data structure trees over the next couple of weeks. In fact, the next 3 weeks, because next week we are going to cover something called balance trees, and then we are going to see heaps, which is also a certain type of trees. So what is the key distinction between these trees is basically they have different structures, and they have different properties, which is they maintain some certain properties which are helpful for certain operations. And we are going to cover like why is that particular tree needed in the first place, like what were the issues with one tree and that gave rise to another, just like what we did to the linked list, which is why do we even need a single linked list with a tail, and then why do we need a double linked list, because it was kind of solving the problem as we were moving forward. So similarly, we are going to see the similar type of structure or in the organization of the lectures, which is why do like we need specific different types of trees. So let's start with the most generic type of trees, which is something called an n-array tree. So an n-array tree is a tree with each node consisting of at most n children. So what I mean by that is like there has to be just one root, because that is one of the key statements of a tree. So a tree is still following those three properties. Every tree has to follow that three properties. But now instead of two children, which we were seeing earlier, this can have n number of children. So there could be n number of children. And similarly, like each of the children, which are its subtrees, can also have like n different number of children. And this is basically recursive. So most of the tree definitions we are going to see is recursive, which is they propagate downward to all the elements of its subtrees, which is let's say if we are talking about an array tree, which is the root element, it will propagate to all its nodes. So each of its nodes are also an array trees in its own right. So this is an example here. You can see like we have uh, this example, which is an array tree. Again, like they could be multiple nodes, and they could be at most like n nodes, or at most n children at a particular level for this particular uh, tree. The next type of tree is the binary tree. So binary tree is basically a node consisting of at most two children. So you have either one child, no child, or two child. And this is again like recursive, which is you could have two here, you could have one here, but you cannot have something like three here. Like that is wrong. That defies like what's in the definition of binary tree. And in general, like an array tree was a more generalized version. While if somebody asks you what is a ternary tree, basically a tree with at most three children. And similarly, if somebody asks you what's a quadernary tree, which is quad is all these are Latin acronyms, so or prefixes that are added. So quad is basically four, like it can have at most four nodes, and then if it is pent, it means it can have at most five nodes. And when we are going to cover like b plus trees in the next week, you're going to see like we use more than two children in some of the trees, and why there's a need for that. So in this case, like again, this is a binary tree because each of the node has at most two children. 25 has two children, 2 has one, and 51 has one. The next one is full binary tree. So a full binary tree is a binary tree where all nodes have either two children or zero children. So I'll give you an example, which is this is a full binary tree, even this one, because if we talk about this, this has two children, this has two children, this has zero children, and let's talk about this one. So this is again a full binary tree because again this node has two children and this one has zero children. Now you don't have to memorize all these definitions. We are going to give you these definitions in the exam if we are asking questions, but you need to identify whether a tree is like a full binary tree or not, or if we ask you to write pseudocode on checking like whether it's a certain type of tree, you should be able to write code if we have given you this entire definition. So again, like, you do not have to memorize all these definitions, but if you are given the definition, you should be able to identify whether this tree falls under that definition, as well as we can ask you to like write pseudocode to do some operations on that particular type of tree. So this is an example again here of a full binary tree. 25 has two children, 2 has two children, uh, 51 and 11 have no children, 11 has no children, and 5 has no children. So technically, this tree, like technically, when we are going to talk about later, when we are going to talk about elements, generally when we are talking about binary search trees or other different forms of trees, usually we do not allow repetitive elements. Some trees allow that, but generally we do not allow elements to repeat in the tree. So for binary tree it's fine, but like when we discuss some certain type of trees, they do not allow duplication. The next one is perfect binary tree. So perfect binary tree is a full binary tree of height h with exactly 2 to the power h minus 1 nodes. So you can only have perfect binary tree if it is filled up to the last level, which is, you cannot have like zero children in this case, because if you have something like this and now the height is 3, so the number of nodes will be 2 to the power 3 minus 1, which is 7. So this is not a perfect binary tree. So to make it perfect, you need to have 7 nodes. So in general, all perfect binary trees would be filled up till the last level, which is, this is a perfect binary tree. So is this one. So is this one. And so is, like, if I make another level that is completely filled, then that's a perfect binary tree. Now, one important property of perfect binary trees is it has uh, a perfect binary tree with n nodes. Like if the number of nodes is n, like in this case there were 7 nodes, in this case there are 15 nodes, in this case there are 3, in this case there are 1, the height of the tree is utmost log of n, which is, in the, it has to be actually O of log n. Uh, there's actually a proof that is theta of log n, so I'm not going to cover proofs, but generally we can find the height of this tree by just taking a log of 7, and that would give us the minimum number of height, which is like log of 7. If we take the base 2, if this is smaller than log of 2 base 8, which is 3, because we have 2 to the power 3, like this can be written as 2 to the power 3, so which is 3. So log of 2 base 7 base 2 is basically less than 3, or the height is basically 3 in this case. Again, this is another example given for a perfect binary tree. In this case, we have height 3, so we can calculate the number of nodes by 2 to the power h minus 1 in this case. The next one is complete binary tree. So complete binary tree is a perfect binary tree through levels n minus 1, which is, earlier we had n levels, but now we have n minus 1 levels that are completely filled, and the last level can be unfilled, which is, but all of them should be pointing towards left. So this is perfectly a complete binary tree, but if we erase this node, then it is not a complete binary tree. And why is that? Is because the last level, which is like this level, should be filled from left to right. So you have this node, but you don't have a node on its left. So to make it complete, we need a node on the left. And again, the height of a complete tree is also given by the formula O of log n. And usually when we are performing operations on a complete or a perfect tree, uh, basically we know that it will most of the operations can be performed in O of log n. So question to ask is a full tree complete, or a full binary tree that we discussed, is that complete? And is a complete tree full? So just think about this question and try to practice. If you have doubts, let's discuss in office hours, but this is a nice question to think about. So if that's the case, like you should think about what are the examples where they are same, what are the examples where they are different, and you can use a comparative approach to discuss. So this is another example of a complete binary tree. Again, you can see like these nodes are filled for n minus 1 levels, while for the last level, it's filled from left to right. The last type of tree that we are going to discuss is called the binary search tree. So this is a special case of binary trees. It is basically a tree where all values of the node's left subtree or descendants to the left are less than the node, which is in this case, like let's say if some value is there in the node, like let's call it 55, everything that is there on the left side or the left subtree is going to be less than 55. And everything that is there on the right hand side, it's going to be greater than 55. And for the sake of the course, we are going to assume that there are not going to be duplicate elements in the trees. Like let's say if we are designing this data structure and you want to store duplicate elements, you can basically keep a count variable when you're defining your node class to keep a count of how many 55s are there. But for the simplicity, everything on the left subtree is less than 55 and everything on the right subtree is greater than 55. Also, it's like an ordered binary tree because let's say if we are trying to search a value in an example was this binary tree, and there's no way, like let's say if I want to search, like let's say a value 35, if there's no order in this, I have to search each node and check. But in this case we have some order, so just like binary search, we can just reduce our steps into half by just traversing either right or left based on this ordering. So again, this is an example given of a binary search tree. Here you can see that 25 has two subtrees. Everything on the left subtree, like you can see, is less than 25, and everything on the right subtree is greater than 25. Similarly, like this definition propagates downward, which is each of these nodes, which is 12 itself is a BST and 51 itself is a BST, which is in this case, everything on 51's left is less and on the right, there's nothing, but if there was, it should be greater than 51. Similarly, everything on the left of 12 is smaller and on the right of 12 is greater. So you cannot have a value something like 34 here, like although it's greater than 12, but you can see that this 34 is greater than the root node. So if you see, this defies our first property that everything on the left of the root, which is all nodes of the subtree, should be less than the root node. In the next video, we are going to specifically discuss about binary search trees, their properties, how we insert, delete, and traverse or search in a binary search tree.